Innovation, interoperability and infrastructure, the 3 I's. So important to get smart metering right so that the smart grid will naturally follow. But the UK has been working on this since 2006. Why is it taking so long? True, we are one of the only markets in the world where the energy retailer is the contractual hub for metering. Everywhere else it's the network business. But we haven't really seen true innovation elsewhere either. How can we turn this around? Hello, I'm Nigel Orchard, CEO of Pilot Systems. We've been running for 25 years, helping meter vendors, energy retailers and their downward supply chains achieve interoperability, whilst maintaining their value add, essential for innovation. We've done this with the FLAG protocol, the fundamental of modern protocols used today, such as DLMS and Zigbee Pro. And I'm going to tell you the secret about why our product, CHIRPS, continues to serve the energy business community longer even than Microsoft Windows. Here's something we prepared earlier, a meter simulator. On the left, you see a typical single-phase meter with the display showing time. You can click through the displays using the push button. But now let's have a look on the inside. The meter's memory map, or list of logical addresses. This is how the data is stored in the meter. You can see the time incrementing at the lowest address, and then you can see the other registers too, and various address locations, and in various formats. So how does the FLAG protocol fit in? Well, the beauty is that it's generic. In other words, it does not specify features or functions, just the raw data. That means its specification and scope is very small, and also that it can support any feature or function a meter manufacturer may want to include. Let's take a look at an interrogating device on the right-hand side. Firstly, we connect. In the demonstration, this is via local IP, but in reality it could be a modern connection, GPRS, or a two-way pipe provided through RF or power line carrier. In any event, once you are connected to the meter, you can log on using the standard logon sequence. The meter replies with its 3-digit sign-on code. These codes are reserved for meter vendors, a bit like a domain name. There are over 700 codes registered. Also returned is a 16-character ident, which gives you information about the meter type and version, and possibly its software version. You can then go through a series of password exchanges to establish a privilege level with the meter. But for now, let's go straight on to reading from the meter. Let's read the first 16 words starting at address 0. In fact, we've read twice as much data as we needed here. Actually, we only needed the first 8 bytes, and remember all the values are shown in hexadecimal. The FFs shown in the memory map merely represent empty data areas. Another thing to notice is the interrogator has logged the meter vendor and its type, including version number. A good old SMETS 1 meter. Already 2 million installed in the UK, but sadly not yet interoperable. So that if you change energy supplier, the meter either operates in dumb mode or is replaced by the new supplier. Very nice for the meter vendors who get to sell meters that go on the skip, but not so interesting for the consumer when he realizes that it's happening. Anyway, back to the technology. Let's write 16 bytes of data to address B0. You can see in the left-hand frame the digits at the bottom left change to 1, 2, 3, 4, etc. This could be anything, of course. Tariff times, display sequences, configuration of the meter. It's up to the vendor to format his own data, which is why the protocol is so elegant. He doesn't have to consult anyone else or conform to someone else's specification. Okay, this time let's read a register. How about the main energy import register, which is stored at location 20 hex? Let's read 4 words, or 8 bytes. Now the data has come back, 8 bytes, but it doesn't really mean much. Let's go back and have a look at the display. Well, E1 doesn't bear too much resemblance to the memory we have just read because it needs decoding. Another meter vendor might store it in a different format and at a different memory location. So what's the trick to ensure that the user gets the right data in the right format? Well, first of all, let's just summarize. Here you can see the basic meter with the three interfaces normally provided. An isolated optical port, an RS-232 port, normally available under the sealed terminal cover, and an engineering interface, serial, for transfer of data to and from perhaps an intimate comms hub, something we Brits have called a comms module that forms part of the meter as a plug-on device or option. Now, what I am suggesting is that all these interfaces should be FLAG compatible at the lowest level. The interface would then be simple. Engineers could carry on and design meters without worrying what the upstream system is going to require. I should probably say at this stage that most FLAG meters now do not use memory addressing. That was when processing and memory power was at a premium. Now it's normally logical identifiers that are used. But the principle is exactly the same. The format or functions is not defined, here anyway. They could be DLMS messages, or OBIS, or MBUS, or whatever. So we have a meter and fully functional communications. These could already be installed on the wall. The comms hub could come later when the communication systems have been proved. But what is the communication system? Well, probably one you have seen already. The only difference here is because the reading system does not know the meaning of the data it is reading, it needs some kind of lookup system to help it. These are provided as scripts from the manufacturer that operate with the world-famous software kernel, CHIRPS. You will have probably seen CHIRPS if you've worked with British Standards meters. It's integrated in many vendors supporting systems. The Elster Power Master Unit and Itron Indico Master Station are typical examples. Or perhaps you have seen a meter operator running CHIRPS on his handheld computer. In any event, all the UK meter vendors use it and know it well. Elexon, the balancing and settlements agent in the UK, use it for technical assurance of their meters. It's used by offshore energy suppliers and network companies who want the functionality of a UK smart meter but don't want to wait around until the Great Britain Companion Standard or GBCS finally arrives. It would be a very long time. But let's get back to technicalities. Here you can see CHIRPS communicating with a meter using FLAG messages stored in an instruction script and collecting responses in a similar script. Scripts in a common structure but still with manufacturer-specific function and format. But now the vendor can translate these scripts to meaningful data. This is done at the head end. The customer can use support software from the vendor itself, or pilot systems will happily prepare CHIRPS scripts based on customer requirements. Either way, the customer now has a facility to operate with any vendor's meter that meets the functional specification he requires. So, let's go back to the meter and read those registers using CHIRPS. First, we must log off from the meter and terminate the connection. The meter is now ready to be interrogated by CHIRPS. Let's click over to the second tab on the right-hand side and see CHIRPS running with the instruction and response scripts that it uses. Here is the pCHIRPS version normally used by a head-end system or within a meter vendor's master unit. Since there you know the meter you're communicating with, you can pass it the network parameters you need, phone number or IP address, and the name of the script you want to run. The script we will now run reads the main registers from the meter. OK, let's have a look. you can see that address 20 was read as before, but the value underneath now corresponds to the value shown on the meter E1. OK, let's have a look. You can see that address 20 was read as before, but the value underneath now corresponds to the value shown on the meter E1. That's because it's been translated using the script. This is the script provided by this vendor to perform this service, reading the main energy register. Of course, that is the simplest and most fundamental thing you might want to do with a meter, and as such, it is the easiest thing to define in a specification like DLMS or Zigbee Smart Energy Profile. But where these protocols fall over is when you need to define more complex functionality. The meter vendors design in different ways from each other, and no matter how long you put engineers from competing vendors in the same room, they will not agree on a fixed and detailed specification that could be used to define an infrastructure. They've been doing that in the UK for the last 9 years, and we still don't have a smart meter that is interoperable. Using CHIRPS with scripts from each manufacturer means they can get on with their own job and innovate, rather than having to discuss their design with their competitor. What you have seen there is CHIRPS reading the basic set of energy registers from the meter and translating them to the correct format using a script. And note that CHIRPS could be running on a handheld terminal or as part of an in-station head end. The scripts are identical. Scripts for all the different meters supported are stored and updated every time a new meter is installed. That means the meter vendor is in full control of the value he is adding. You don't have to wait for a new TIM module from a multi-vendor system or come to Pilot Systems for the new protocol. The meter vendor can provide it directly. For now, CHIRPS is in use with handheld and for online reading through the PSTN, PACnet, GSM, GPRS and IP. But we also have firmware version that will run on a comms hub. This opens new possibilities for an interoperable smart meter infrastructure based on powerline carrier or radio or whatever else. Whilst FLAG is a ping-pong protocol that requires continuous online time, CHIRPS, on the other hand, is the single transfer of an instruction script and a response script. In fact, even easier, the instruction script need only be transferred once and then referred to as required. This means that any CHIRPS-compatible meter can be supported by a communication system that is able to transfer the small CHIRPS scripts up and down. And it's future-proof because it has no visibility of the content. Necessarily, of course, it may need some visibility of network information or certain meter registers, in which case it can also store some CHIRPS scripts provided by the meter vendor for that purpose. Devices such as in-home displays, IHDs, or consumer access devices, CADs, can also take advantage of CHIRPS to provide the connectivity to all the meter types and variants necessary. And vendors of auxiliary products such as temperature sensors and load switches can bring them to market without having to know too much about the system they are working with. Just FLAG compatibility and a few of their own defined FLAG messages is all they need. Here you can see CHIRPS integrated directly into a comms hub, providing the local translation necessary for an IHD or CAD. CHIRPS is a very small footprint, about 50k executable, and the vendor scripts are typically 2 or 3k in size. So inclusion of CHIRPS in the comms hub is a very practical way to provide the interoperability and connectivity so badly needed by smart meter programs like the one in the UK. Finally, it's probably worth mentioning why the UK smart meter programme is not working. Here you can see all the stakeholders for the specification of data items for the meter. For the system to work, these must be specified in complete details, not just the data, but any functionality that acts as a result of the data change. Meter vendors have been struggling to agree this with DLMS, comms vendors with Zigbee, and suppliers with the DCC User Gateway or DUGIS. Then what about the poor old consumer? After all, he is paying for this initiative. About £2 billion spent so far with not much to show for. The table shows arbitrary figures, but the light blue at the bottom is where we should be at 100% in order to roll out a system, with the dark blue where detail still needs to be agreed, and the green where items are either new or redundant. You can see that we will never actually get there. The system will be obsolete long before it is ever complete. Of course, you do need to specify data items so that IT systems can be built around them, and it is right to have an industry group doing this. But the system must not be dependent on its completion before it can be cut in. We must establish the interoperability first and let the market innovate afterwards, not the other way round. Markets innovate, not standards committees. They just follow trends. Or should do, unless they are controlled by powerful commercial players. CHIRPS is an ideal platform to provide that interoperability and let the markets test out energy best practice functions and features. The successful ones will be retained and the unsuccessful ones will fall away, but we will all be pulling in the same direction. How can we make this work in practice? Well, energy companies and regulators must specify FLAG and CHIRPS compatibility, which would ideally be set up as an open standard. To be CHIRPS compatible, a meter vendor should be able to perform all the communication functions of the meter through CHIRPS, providing the instruction scripts and accepting the response scripts for decoding. These could be issues as drivers on a CD, just like a printer driver for a PC. So, we do hope this presentation has been useful. The software you have seen form parts of FLAG and CHIRPS development kit, available under license to meet vendors and ancillary equipment manufacturers. The software and interfaces have been proven over the space of time to serve all stakeholders in the industry and will be key to an infrastructure that provides both interoperability and innovation. Thank you for watching.